Hello everyone, and welcome to this episode of chemistry class. And in this episode we're going to talk about orbitals, electron configurations, and a brief little word about the periodic table. It all fits together really nicely. Let's start with orbitals. And this, as it says, is the start of an orbital map. And it shows the start of where electrons could be. And these are just representations of the wave functions of those electrons. These are just weird shaped orbitals, and you got to think of an orbital as just a place where electrons can kind of hang out. And yes, they have weird shapes, but just go with it. And it's going to hang out there most of the time. There's possibility that the electron might be out here somewhere for a short time and out here, but most of the time, 90% of the time, 95%, it's going to be within that little area or volume. And electrons are uncertain, so we just kind of have to go with regions of probability. And what we need to know, yes, they come in weird shapes. We're not going to have to draw them very much. But we do have to know they come in different types. You'll see these three are spherical, and they're centered around the nucleus, and so we're going to call those s orbitals, the 1s, the 2s, the 3s. And the way this is spread out, we're working on energy levels. The first energy level only has one orbital, and that's an s orbital. The second energy level has 4 orbitals. One round one, like this one, and we call it the 2s because it's on the second energy level, and 3 matching 2p orbitals. And those are oriented kind of perpendicular to each other, but they look like figure eights or infinity signs or whatever. But an electron in that spot, in that orbital, can occupy any part of that anytime it wants to, and sometimes leave and come back. The third energy level has 9 orbitals, and we'll have the 3s. Notice it's a little bit bigger than the 2s. Followed by 3 identical 3p orbitals, third energy level p. And then on the third energy level we introduce these d orbitals, which look like clover leaves, and then this one's kind of unique by itself. But again, the electrons can occupy any one of these. And so it gets us to the question, well, what if an atom has a bunch of electrons? Which of these are they going to occupy? And are there any ways of us to predict what they're going to occupy? And yes, there are. There's actually 3 different rules for predicting electron configurations, and we're going to model those next. We're going to start with a simpler element, and that element is going to be fluorine. And for simplicity, we chemists, even though we try to envision orbitals like this, for simplicity we often just use boxes to represent those orbitals, even though they're actually not boxes. But that said, we want to know, well, what is fluorine's electron arrangement going to be? And fluorine, first thing we need to know is how many electrons does it actually have? And fluorine is element number 9 on the periodic table. So it has 9 electrons. There's fluorine right up there, element number 9. And that's how you find out how many electrons it has. Well, okay, where are all those 9 going to go? Well, there's 3 rules. The first is called the Aufbau principle, and it might make sense right away. We're going to start at the lowest energy possible and work our way up. We're going to fill this box first, then this one, then these, and just kind of work our way up the ladder this way. The second rule is called the Pauli exclusion principle, and that is that up to 2 electrons can fit per orbital. So 2 can fit in this box. I have 9, so I'm going to have to fill more than 1 box. And we're going to use an arrow to represent an electron. And this electron is pointing up. The Pauli exclusion principle says you can fit another one in there, but it's got to be pointing the opposite spin, the opposite direction. And we just use arrows because they imply that electrons are moving, and these are moving opposite of each other. So there's the first 2. Aufbau principle, that's filled by 2. We're going to go to the next one. This is our 3rd electron, our 4th electron, and then the next energy level is the 2p's, and that's where the 5th electron comes in. But this is where the 3rd rule kicks in, because we have another several electrons to put in there. And the 3rd rule is called Hund's rule. And Hund's rule says, just like people when they ride the bus or ride the train, and they don't know anybody else, they're going to take the empty seats, 1 per seat, until they start doubling up. And electrons are no different. Because we have 2 p orbitals here, we're just going to put the next one in here because they repel each other, and it's just going to want its own orbital. So now we have 6, here's 7, and then we have 2 more to go. Then we start doubling up, like people on the bus. Once everybody's got their window seat, we double them up. And so, following the 3 rules, fluorine's configuration looks like this. And we can write it out in sort of a line form. The written configuration is just a list of the orbitals and how many electrons are actually in each orbital. So for fluorine, in the 1s, there are 2 electrons. In the 2s, there are 2 electrons. In the 2p, there are 5 electrons. And that is our electron configuration for fluorine. It represents where all 9 electrons are. 2 in there, and 5 in there. Next, let's try an element with a few more electrons than fluorine. Let's do iron. And the important thing to notice is that as we do these, the same pattern applies. No matter how many electrons you have, you're going to follow the same 3 rules. Now, iron is right here in the middle of the periodic table with 26 electrons. And so we just need 26 arrows in our diagram here. So we're going to have to go a little farther than we did for fluorine. So 1, 2, 3, 4, remember 1 per orbital, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And then here we jump over to the 3Ds because they're next. And again, 1 per orbital, 21, 22, 23, 24, 25, 26, and we're done. So the configuration for iron has all of these jammed full of electrons, whereas we've got these 3Ds with some all by themselves. Again, following the rules. Writing out its configuration, 1s, 2, no punctuation here is necessary, 2s, 2, in the 2p's there's 6, in the 3s there's 2, in the 3p's there's 6, the 4s there's 2, and in the 3Ds there's room for 10, 2 in each, but we've only got 6, so we're going to end with 3D, 6. Let's do one more, and that is going to be the element strontium. Now, strontium has a few more electrons than iron. It's got 38 electrons. You can check your periodic table for that. And so we just need 38 arrows. The nice thing about electron configurations is that once you start doing them, it's a lot of repetition, and once you kind of learn the rules and learn the patterns, they go pretty quickly. I'm up to 18 electrons, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. I got to still go with 38, so we're going to go 31, 32, 33, 34, 35, 36, 37, and 38. If I write this all out, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, and then 5s is last with 5s2. Okay, so you might have noticed something as we're going along, and that is that fluorine happens to be, its configuration ends in 2p5, and fluorine happens to be in the 2nd row of the periodic table. Okay, strontium's configuration ended in 5s2, and strontium is down here in the 5th row of the periodic table. And you might be wondering, is that just a coincidence? Well, no, it's not. Because if you've ever wondered why the periodic table looks the way it does so because of electron configurations. Okay, I'm going to swap out my periodic table for a different one. And that's this one. So it turns out that there are 4 areas of the periodic table. They all correspond to the 4 types of orbitals. These 2 tall columns over here represent the s orbitals getting filled, s1 and s2. Everything in this column has 1 electron in its outermost s orbital. This one has 2, but then it's filled, so we have to go on to the next. And now up here, we're going to go over here to the p's. The 2 p's would come next, and so on. And this is great because it allows us, once we know the periodic table and really understand its pattern, it allows us to not have to memorize electron configurations. Okay? Look where fluorine is. If we think of this as the S block, the P block, which has 6 columns, because 6 electrons can fit in the P's, 10 columns in this D block area, because 10 can fit up to 10 can fit in the Ds, and the F's can fit up to 14. Things get a little weird down here, but don't worry about that for now. Look where fluorine sits. That's fluorine's box on the periodic table, and guess where it is? It ends in 2p5, and it lives in the second row, P block, 5th column over, 2p5. So if you do your configuration and you get to the last term, whatever the last term is, think of it as its row, block, and column, and that's its home on the periodic table. Strontium ends in 5s2, so guess where it is? 5th row, S block, 2nd column. That's strontium's box. Iron's configuration we did, it ended in 3d6. So as we read the periodic table left to right like a paragraph, 1s, then 2s comes next, then the 2 p's get filled, then the 3s, then the 3 p's. But because the 3ds start the process of they're a little higher energy than the s's, the 4s comes first, so we tuck the 3ds down a row where we think we should have had them. But after the 4th row S, comes the 3ds, 1, 2, 3, 4, 5, 6, and that is where iron lives on the periodic table. It's in the 3d row, 6th block, D block, and 6th column over, and that's its spot. So on the other hand, you can actually predict a configuration based on its spot on the periodic table. So if I were to pick, for example, indium, this one, I already know based on its location on the periodic table, 5th row down, P block, 1 column in, that its configuration is going to start at 1s2 and then 2s2 and 2p6 and work all the way up to 5p1, and that's where it's going to stop because that's where it lives on the periodic table. So there you have it. There's a lot of information here, and it's something we have to practice and get used to. But once you understand the patterns here and in the patterns in an orbital box diagram like this, electron configurations get a lot easier. So good luck, give them a shot, and let me know if you have questions. Have a great day.